is Nar Ganapathy and I work in the base group on IO. Today I'm going to talk about 6 drivers for 64-bit Windows. If you look at the issues for drivers for 64-bit Windows, there's going to be some kernel issues for 64 bits, and then there are generic code issues for 64 bits. So there will be, so you can see that the talk is kind of distinctly divided into two. So my talk will be broken down as follows. I will initially talk about 64-bit Windows, why are we doing it, and what are we achieving by going to 64-bit Windows. I will then go into the details of the programming model. The programming model for 64-bit Windows is pretty simple, and there are only some new types that have been added, so it should be pretty simple to understand. And after that, I will go into the specific coding issues. There are driver-specific coding issues and generic programming issues. The driver-specific coding issues apply more to hardware drivers. So I don't know how much of that applies to filter drivers. But if you guys think that they're interesting, just let me know. Otherwise, I will skip past them very quickly. So why are we doing 64-bit Windows? By moving to 64-bit Windows, we obviously can benefit from the larger space. We can scale our applications seamlessly from machines with small amounts of memory and CPUs to machines with large amounts of memory and CPUs. The significant goal for 64-bit Windows is to make sure that the porting of software from 32 bits to 64 bits is as simple and easy as possible. Our goal is to have a single source code base that works on both the platforms with no if-defs or special case code for 64-bit Windows. Note that we do support 32-bit applications on 64-bit Windows, but we don't support 32-bit drivers. So any driver that has to work on 64-bit platforms should be ported first. So let's go into the details of the programming model. The 64-bit Windows programming model is pretty much the same as the 32-bit Windows programming model. There are the same APIs. The DDK is pretty much the same. The semantics are exactly the same. The only difference is that we have added some new types. As I said, the goal is to make the porting simple and easy as possible. So we have just changed the size of pointers and longs to 64 bits and nothing else. So the size of other basic types like integers, longs, characters, and shorts, they all remain the same on a 64-bit platform and a 32-bit platform. We call this the LL64 programming model. In Unix, you have the LP64 programming model where longs and pointers are 32-bit or 64 bits. The reason we did this is because if you look at the source code on Windows, a lot of them use dwords and longs, and if you change the size of dwords or longs to 64 bits, then the porting it becomes very difficult to port existing software to 64 bits. So as I said before, all the DDIs and APIs work pretty much the same as on a 32-bit platform. To ease porting, we have also added some new explicitly sized types. So with these new types, the size of the type is you pretty much know when you actually write code. So we actually divide the types into two categories: fixed width types and pointer precision types. So fixed width types have the same size on both the 32-bit platform and a 64-bit platform. Pointer precision types take the size of the pointer on the platform they are on. We will go into examples in more detail. So in addition to the new types, we also added a change from APIs to take a bigger type. So for example, all memory allocation APIs now take a 64-bit value for length. So now you can allocate more than 4 gigabytes of memory with a single call. Now, on the other hand, we have not changed the length of I/O operations. So when you do read file, the length that you pass for the read will be 32 bits on a 64-bit machine even now. Again, we have made all these decisions on how the APIs are structured before and how easy it is to port the software from a 32-bit platform to a 64-bit platform. So this slide gives an example of fixed width types. So if you define a variable of this type, then the size of the variable is the same on a 32-bit platform and a 64-bit platform. So if you have an integer of type int64, then it is 64-bit wide even on a 32-bit platform and 64 bits wide on a 64-bit platform. So you can use, if you have like fixed structures, fixed size structures, then it's better to use fixed width types. These new types take the size of a pointer on the platform they are compiled for. So a variable of type int pointer is actually an integer, but it is 64 bits wide on a 64-bit platform and 32 bits wide on a 32-bit platform. The goal of these types is so that they can always carry the size of a pointer. So we have lots of code in Windows, whether you like it or not, which actually exchanges pointers and integers, mainly for arithmetic and doing logical operations and so on. And using pointer precision types, you can actually port that code from a 32-bit platform to a 64-bit platform very easily. So if you look at the basic porting issues, the biggest issue is this change in size of a pointer, and obviously that is the only thing that is the only major difference from a 32-bit system. So the key goal is to use the pointer precision types and go through all your structures that contain pointers and do the right thing. If you divide up the porting topics, there are specific driver issues and generic programming issues. The programming issues are common for both applications as well as drivers because they just generate types and how do you allocate memory and how to do storage and so on. So let's go into the driver issues first. So in the kernel on a 64-bit machine, we have a huge address space. Now the values given in this slide are specific IA64, and it can change from processor to processor. So if in the future we actually port a 64-bit version of NT to a different processor, then these values might differ. But this slide gives you an idea of how big the address space can get. You have a very large paste pool, a large amount of non-paste pool. So the amount of memory that can be allocated by a driver is now limited by the actual amount of physical memory on the machine as opposed to the virtual memory limitations of an x86 processor. One of the key porting issues is actually caused by our x86 support. As I said before, on 64-bit Windows, we actually run x86 32-bit binaries. And this support is actually provided by a subsystem called the WOW64 subsystem. This is also called the Windows on Windows 64 subsystem. And the way WOW64 does x86 support is actually by a process called thunking. And by thunking, what it does is, it basically takes all the APIs that transition from a 32-bit process in user mode to a 64-bit kernel, and it actually stretches the parameters of those APIs to 64 values. If you look at the DLLs that are really thunked, only the lowest level DLLs are thunked. Many high-level DLLs are actually just stock x86 binaries. So for example, NTDLL or DLL, user.dll and GDI.dll are thunked, but MFC or even high-level DLLs like COM may be just running unchanged. So these are some implications for for driver writers. For the most part, all the I/O requests that come from user mode can be just handled uniformly by the driver. So for example, if a 32-bit process issued an NT-read file call or a 64-bit process issued an NT-read file call, the difference shouldn't be apparent to the device driver writer. So the code of the driver remains the same. The only exception is the I/O control system call. The reason is that the parameters passed in an I/O control system call is specific to a device driver and the application. Only the application and the device driver know the format of the parameters. And because of this, the WOW64 subsystem cannot transparently stretch the parameters or do the right things. So in this particular case, the device driver has to handle that trunking by itself. So this is probably the biggest issue with regards to coding. Before we go into the I/O control issue, I want to say that with 64-bit Windows, we're actually removing a lot of legacy support for discovering devices and stuff. So in theory, those issues shouldn't be there for file system filters because they shouldn't be really dealing with hardware. But in any case, you have to support plug-and-play and power management ERPs, which again should be just straight away passed through to the base file system and to device drivers. And I don't think DMA really applies to file system filters. So let's now go into the I/O control issue. So if there is an I/O control that is supported by the drivers and that has got structures or parameters that are either pointers or pointer position types, then those parameters have to be thumped by the device driver. So in this case, the driver has to know whether the I/O request or the OR came from a 32-bit process or a 64-bit process, and it has to go and look at the parameters and validate them correctly. There are several methods of distinguishing between the I/O request and who the caller is, and 3 ways of doing it. The first method is to actually avoid any pointer position types at all in your pictures. This may be hard to do if you have binary compatibility or you have other issues. The second method is to use the API. I/O is a 32-bit process. Now, if you use this API and you pass the OR as a parameter, then this API will return true if the original OR issued by the I/O manager came from a 32-bit process. So then you know that if it was an I/O control, then you can look at the buffer and you know that it came from a 32-bit process, and so you can treat it accordingly. A third method is to actually use the new bit in the function control code field in the I/O control. So I have some examples on these two types. So to go into an example, let's look at an I/O control structure which is passed as a parameter from an application to a device driver. So in this I/O control structure, we have a lot of pointer position types. We have a p-wide, which is obviously a pointer. Size t is a pointer position type. It's 64 bits wide on a 64-bit platform and 32 bits wide on a 32-bit platform. And the same thing goes for the handle. So if this I/O control structure was allocated by a system process, it will be double the size of the same structure allocated at the 32-bit process. So if this I/O control request comes to the driver, it can have either of these two sizes, and the driver has to separate them out. So the first thing the driver has to do is to allocate a parallel structure inside the driver source code, which kind of mirrors the original structure field for field. But instead of using pointer position types, you should use fixed width types. And the type used should match the size that would have been if it were allocated by a 32-bit process. So in this case, the first parameter was address, which is a p-wide in the original structure. And so in a 32-bit system, the p-wide will be 32 bits wide. And so we now define this field to be wide star pointer 32. And so the length, which was size t, would be 32 bits wide in a 32-bit system. So we replace that with int 32. Now you do have if you look at the DDK, there is a mapping between these fixed types and the old types like void and what is the new type in the system. So you can do this conversion pretty easily. But I know it's funky. So once you have defined the structure, then it becomes pretty easy. How do you turn on this one?
pause button on there? Very good.
So, sorry for the delay. So in your driver code, the first thing the dispatch routine, the driver first has to call this API, IFS 32-bit process on the ERP that is coming from the IO manager. And if this returns true, then we know that the ERP came from a 32-bit process. So we now cast the structure to our newly defined 32-bit structure and validate the length accordingly. So we compare against IO control underscore parameters underscore 32. And having done that, we then copy the structure from the 32-bit value to a 64-bit structure, field for field. By doing this field for field, we are actually doing the trunking inside the device tower. And after that, the IO control is handled in a straightforward manner, just like it would be for any other IO control. So for 64-bit IO controls, we know that the size will match correctly, and so there's nothing that needs to be done. So it's pretty simple, but you have to look at your IO parameters carefully. As I said, IOS 32-bit process is one method of distinguishing between a 32-bit process and a 64-bit process. Another method of doing that is to actually use a field in the IO control code. If you look at the IO control code as defined by the IO architecture NT, it has got 4 fields. A device type field, there's an access field, a function field, and a method field. Of this, the function field is completely left up to the device type operator. So the driver can define this field into any value it wants. So if you have a bit free in this field, then you can define that bit as a 64-bit bit. And then, so in your header files, you'll have like 2 files for the same name. So one will be def 64-bit, and the 64-bit defined will have this bit set. And so when somebody compiles the code and compiles the application code for a 64-bit system, then when that application issues a request, you know that that bit will be set and you can use that. The advantage of this one is in the iOS 32-bit process, the ERP has to be the original ERP that came from the IO manager. So many times what will happen is the IO manager issues an ERP and it comes to a filter driver, and the filter driver takes the ERP and creates a new ERP, and it may just want to take the structure and pass it down without doing anything else. And so in all those cases, it's hard to carry the thread context around. And so using this method, we can actually pretty easily carry the context. And this method would be applicable in some cases when the old API cannot be used.
Hey Nar, there's a question over here. Did you have a question?
Yeah, I did. In that previous slide where you translated 2-bit addresses to 60, well, you actually rephrase that. You actually acknowledge that you're in a 32-bit, you receive 32-bit pointer. Do you have to translate that pointer to a 64-bit pointer?
No, you won't get a 32-bit pointer. You actually get you'll actually get a structure. If you use buffer IO, then the IO control would actually be, the buffer would be copied from user mode to kernel mode. The address would be 64-bit address. It's just the structure would actually be a 32-bit structure.
No, you had an address parameter in that structure. What would be in there?
Oh, that address would be the address. If that address contained a 32-bit address of the process, then that would be the 32-bit address. But inside the kernel, if you want to access that address, you just use that address and it should just work.
Okay.
Presumably, you have to do the standard stuff like logging and making sure they are the same process context and all those things.
So it's running in the same context as,
right.
As the.
If you're not in the same process context, then you should get into that process context before you can do any operations. I guess don't apply to filter drivers. Should I discuss these things at all, or
Yes.
okay? If the filter driver for some reason decides to use physical addresses, you should note that physical addresses on a 64-bit machine is 64 bits wide, and so there are lots of drivers that treat physical addresses as 32-bit values. Since we are going to have addresses greater than 4 gigabytes, you should always store physical addresses in a 64-bit value, and the type should be physical address all caps. Now this type has always been defined as a 64-bit value on versions of NT. So if you already use this type, then you would be safe. If not, then you have to look at the code and modify accordingly. Then there are some new DMA APIs which have been added called scatter gather APIs, and they would be useful for improving your performance. And the second, if there were drivers, if there were devices in the 64-bit machine which couldn't address greater than 4 gigabytes of physical memory, then you have to double buffer it, because the IO request could have been made by a 64-bit driver, 64-bit process, and it would have had a physical address which was greater than 4 gigabytes. In which case, we have to do some double buffering. First, have to DMA the data into a buffer which was memory less than 4 gigabytes, and then copy it back out to the user process. All these things should be handled automatically if the driver uses the standard window APIs. If not, then watch out. So now we go into generic program issues. The biggest issue is the usage of pointers and integers. And there is alignment, and there are a bunch of cleanup issues like using when we use constants and when we actually cast structures and so on. So let's go into examples. So if there is code which casts pointers to integers, then you shouldn't use the old integral types like int, long, ulong, or dword. You should use the appropriate pointer precision type, like using a ulong pointer and a uing pointer, because otherwise you will actually be truncating a 64-bit value into a 32-bit values, and you will be losing valuable data. And if you do have to truncate pointers, use these macros to truncate pointers, because that way the signing and other things will handle automatically. This is not coming out right. But in this case, we have a structure, the first structure which actually takes a ulong pointer as one of the parameters, and it assumes that since it's a pointer, it actually stores a 64-bit value in there, whereas the caller actually passed it just allocated a ulong as an address and cast that so that it will shut up the compiler and passes it to the callee. Now, because of this casting, we will probably be corrupting the stack, because we're actually storing a 64-bit value into a 32-bit variable. So if you have any casting, and the casting used to work in 32-bit systems, then they may not work in 64-bit systems. So be careful while doing casting. The first one is pretty trivial. If you have -1, this F8F is not the same as -1. Use the macro invalid handle if you want to compare invalid handles. And when doing pointer arithmetic, cast the pointers to a pcar instead of a ulong. There is lots of code in in the system which actually casts the pointer to a ulong and adds the actual value instead of a pcar, and that can cause pointer truncation.
Hey, Nar, go back to that. I don't understand. I mean, pcar should be a 64-bit value. Why is that a problem?
No, this is not a problem. I'm saying this is the correct one.
Okay.
A lot of drivers use ulongs
Oh, I see. Okay.
instead of pcars.
Okay.
So, and if you want to print 64-bit values, use %I. And also note that in a 64-bit system, any address greater than 8 followed by 7 zeros is not necessarily a common address. This is only true for x86 32-bit systems. And so you should use the appropriate macros that are defined in the DDK to check to see if an address is a kernel address or not. Alignment. In x86, if you have structures that are not aligned at the correct boundaries, the hardware handles that automatically, although there is a slight performance penalty. On IA64, alignments are not handled. So the processor generates an exception and we have to handle it. And this is a real performance problem. And so we have made a decision that on 64-bit systems, the structures are not aligned correctly, the system will check. So you should make sure that if there are any kernel references, then they are aligned on the correct boundaries. So let's take an example. In this case, we have this pragma pack1, which means back at the first parameter's boundary. And so what really happens is, if you allocate a structure of this type, then the pointer will start a 4-byte boundary instead of a 8-byte boundary on a 64-bit system. And so if you store something to the pointer, that will cause an alignment fault. So you should be very careful in making sure that you always get structures that are aligned correctly. So, but if you do have structures that are not aligned correctly, and you really cannot change the alignment for reasons like this is actually a hardware register or something like that, you should use the unaligned macro. If you use this unaligned macro, then the compiler will generate extra instructions to make sure that the alignment is always correct. This is obviously better than taking an exception, handling it in the truck handle, but still, this is still slow. So do not do any casting and let the compiler align the structures correctly. And you want to make sure that there are no padding values put in 64-bit structures. Put all your 64-bit values at the front of the structure.
Is this alignment only valid for 64-bit data types, or is it valid for 32-bit data types?
Only 64. I mean, when you take your code and port it to a 64-bit.
No, but you can still have 30-bit type not aligned on the 30-bit address.
If it's a 32-bit type, the alignment applies only to 64-bit values. So, presumably for 32-bit compiler only aligns it at the right boundaries. Alignment is typically a problem if you have two different backing directives for the same structure. So if you have a same header file included in two C files with two different backing directives, then that can cause a problem. But I don't think we have a lot of packing inside the kernel, and so this really is not an issue that much, as much as it's in applications. And obviously, the memory copy APIs will not fault. They always make sure that the references are either on, they do byte by byte copies or make sure that they are aligned. If you have unions with pointers, make sure that the alignment is correct and make sure that the size of the structure is still correct. If you want to read a structure that is shared between a 32-bit entity or a process and a 64-bit driver, then you need to watch out and make sure that either you do the trunking or you use fixed bit types. And also note that if you look at the difference between 2 pointers in a 64-bit system, the difference between 2 pointers can be more than 4 gigabytes. And so the difference between 2 pointers should be stored in a variable that is 8 bytes wide. So watch out for that case. This is an example where the code worked in a 32-bit system but did not work in a 64-bit system. And the reason is that in a 64-bit system, if you look at the structure, the compiler adds a padding between this D word field and the T void field because of alignment. But the first allocation does not take that padding into account, whereas the second one does take that into account. So if you have these kind of allocations, then you should go and change it. So if you have constants, and if your constants are typed longs or other bit quantities, and you are going to do 64 arithmetic on them, then you'll be in trouble. So make sure that, like in this case, we have this constant called page size, which is of type 100 long. Because of this, when we do arithmetic on the constants, we actually get different values. So, for example, this macro is not the same as macro in a 64-bit system because page size is an unsigned long. And so, if you have this kind of constants, then you should make sure that you handle this correctly. For detail, I have actually explained why these two are not the same. Like this is how the left-hand side derives, and this is how the right-hand side derives, and so you know that they are not equal. By the way, a lot of these examples are also there in the DDK, and so you don't have to worry about. And so you have all the details there. If you have arrays and the index into the array is a D word, and again there will be code which used to work on 32-bit systems that won't work on 64-bit systems. In this example, because index is 32 bits wide, index minus 1 is 8x, and so it is minus 1, and it kind of works on 32-bit machines. On a 64-bit machine, because its index is a D word, this is not the same as minus 1, and so you might get an X violation. So in summary, make sure that your drivers support plug and play and power management. There shouldn't be use of legacy APIs, like legacy HAL APIs that have been downgraded in Windows 2000. Make sure that your pointers and pointer usage is correct. And the 64-bit compiler should be able to point out any problems. And so, and there's a lot of detail in the DDK. If you get the Whistler data DDK, you should have all the 64-bit documentation. That's it. Any questions?
Do you have these slides to hand out? Print it out.
I guess I can give it out.
That would be nice.
I'll give it to Dave Girls.